Here we go. So this is like around where we left off, right? We were talking about how we added, this is what we had before. The little adder, we were calling it our ALU because it can do addition and subtraction. 2 registers, and now we have RAM and the address register. Okay? So for the fun of it, let's just do something here. Whoop. So now this is going to be a little tedious because how we're inputting the data, but it is what it is. So let's say let's load into the address register the value 0, right? So memory address 0. Now obviously it starts as 0, but let's just do it anyways. In practice, in reality, when you turn on a circuit, not everything starts at 0. It's going to start as who the hell knows what. So it's not really safe to ever assume that you're starting at 0. So let's put 0 into the address register. I know, we know 0 is going to be there because it's digital, but we don't really know that in practice. So into the address register, we're going to put the value 0, clock pulse. Okay, cool. Now what? Let's do RAM in. What value should we put into RAM? 3. I love it. 1. Huh? Okay, so now there's 3 there, and we're going to do RAM in, address 0, clock, perfect. So now let's do address 1, clock pulse. I put 1 on the data bus, clock pulse to address in. All right, cool. So what should we put in, what value should we put in memory address 1? 10, I love it. 8, 9, 10, RAM in, clock pulse. Perfect. There. So now, what we have, if we right-click on this, we should see 3 and A. 3 is 3 and A is 10. Cool. So let's now add these values together. Let's put them, and to do that, all we have to do is put them into the A register, into the B register, or register A, register B, doesn't really matter. So, okay, go back to, so right now in this value right here, it's still storing 1, right? So let's go back to address 0, address register in, clock pulse, okay? So now we can double check that this actually is storing, yeah, okay, 0. So for memory address 0, let's put it into the A register. So RAM out. Come on. Oh, what a, oh, son of a man. All right, let's start again. I'm going to get a seat this time because it's tedious. Why didn't you warn me? Oh, what did I forget to do? You said hi, people. Can anyone be more specific? What did I forget to do? Yeah, the input toggles at the top, the data toggles. They should have been Z. I put 0 on that line through those data toggles, and then I also outputted from RAM. So I blundered. So let's start again. Okay. All right, so address 0, okay, 0's in there, whatever. We put the value 3 into, let's make sure it's 0. Yeah, okay, RAM in, clock pulse. Now 1, address in, clock pulse, okay. Now we wanted to put 10, which is 2, no. Into RAM in. Holler if I'm making a mistake at any point. Cool, all right. All right, now we're in great shape, right? Oh, shoot. I want to put 1 into the address register. Okay, whatever. Address 1 is already in here. I wanted to go back to address 0, but I'm lazy. So we'll leave it at address 1, and we'll put memory address 1. Do we want to put the value from there into the A or B register? What do we say? A, you want to put it in A? Okay. So RAM out, A in, clock pulse. So right now, A is storing 0. Clock pulse, A is now storing A. Perfect. Okay, these little pop-ups are quite obnoxious right now. There we go. Okay. Now we need to go back to address 0. Okay, address in. Clock pulse. Perfect. Go back up here, set these to Z. All right. Whoop. RAM out. B in, right? So now we want to take the value at address 0. Why did Y 0? Well, that's what's in the address register. That's 3. We're outputting that. And then B, so we want to put here. It has 0. We clock pulse. It should be 3 now, right? Yeah, cool. Great. So let's turn this off. Turn this off. Well, now the value right here should be, D, which is A, B, C, D, which is 13, right? So now we have the value 13. What do we want to do with it? Where should we put it? We've got options. Where do we want to put it? RAM address 2. Okie dokie. This, by the way, way too late. All right? I've already given you all the last warning weeks ago. You get another one because it's after reading week. That's it, though. You show up this late again, I'll say goodbye, and you don't come in. All right. Address 2. Address 2. Put it into the address register. Clock pulse. So now this has 2. Good, good, good. Turn that off. Very importantly, set these back to 0. All right, good. And so now what do we want to do? We want to do, you know what, for fun, let's do 10 minus 3. What do we think? Yeah, let's do that. How do we do that? Well, we want to do subtraction, which means this should now be 7. Perfect. A minus 3 is 7. ALU out, RAM in. Okay? And then clock pulse, right click. There it is. The 7, address 2. There we go. The big takeaway about this, if it wasn't obvious, is we are moving data around and performing some basic addition and subtraction. That's computation. And we're achieving this by just manipulating signals, high, low. Some of those signals that we were manipulating, and this is very important to recognize, some of those signals that we were manipulating were data, 0, 1, 0, 1, the number 3, the number 10. Some of those signals were data. Some of them was still data, but it was like, it was data for the instructions for like what we were doing, like which memory address, right? So it was still data, but it was data for the steps involved. And some of the signals were just zeros and ones toggling which components were inputting and outputting. So these signals all have meaning, but what they mean really depends on, well, what are they for? What are they doing? What are we encoding? We're encoding what to move where. We're encoding data. They're all zeros and ones, but depending on how they're used, they have different meaning entirely. Some of it's data, some of it's like in instruction. Instruction being like how we move things around, which is pretty cool. All right, yeah. And if we go back to this, now comparing it to that simple as possible design, we have the registers and the ALU and RAM in that. And like I was saying last time, I was originally thinking of putting everything on one side, and I thought that would be nice in terms of like the clarity of the layout, but that just, the computer would get way too big, and so it wasn't really great. So we went with this strategy, and I'm just having it align with this design that I stole from Wikipedia. Okay, and then here's like showing an example of, what is this one doing? Load 15, 4, and 7 into RAM addresses 0, 1, and 2. That's what that does. That's the control signals for doing that. Well, some of them are control signals, some of them are data signals, one's a clock pulse, whatever. Any questions? And then I think here I'm saying, okay, load data for addition and save the result back in address 3. Great, cool. And then load data for subtraction and save the result address 4. Cool. So we're just playing around. But all of these signals are moving things around, and we're performing some task. And if everything worked based on that program, that's what we would see. Cool. Any last questions? Yes?
Can you go over like how that graph or that chart works? Like, so all of those things are happening at the clock pulse?
So yeah, what this would mean is, like, okay, if I want to load 15, 4, and 7 into RAM addresses 0, 1, and 2, okay? So what that would mean is I need to set the address signal high. RAM in and out are, I'm doing it for the sake of space. I have one column for RAM, input, output, just because. As we go, I'm going to kind of like condense these charts just because of space. RAM, input, output, A, input, output, they're all low. And we want to load in 0 into the address register, clock pulse. Now we know 0's in the address register, so it goes low, input high, nothing, nothing, nothing. I want to put in 15, clock pulse. Address high, nothing else. I put in 1, clock pulse. This is just a table showing what we were doing, but this is like the tabular way of kind of like representing it. Does that clarify? Yeah. I mean, there's a lot of steps here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There'd be like 18 steps, 18 clock pulses to do what we wanted to do here. And you might notice too that like, okay, load 15 into address 1. You might notice that like, that took multiple steps. Even though it's like, oh, that's one instruction, load the value 15 into address 1. Well, there was actually several steps. I needed to specify the address, then load the value in. That took 2 clock pulses. So one step is not necessarily like one clock pulse. That's an important thing to notice as well. In fact, it's very common. And a little spoiler, we call these like sub-steps microcodes, which I think is kind of fun. But more on that later. Okay, now 7 segment displays. We're taking a bit of a step away from like the computational aspect and looking more to like, okay, peripherals for our computer. How can we, it's still like an important exercise of like encoding and thinking, how are we going to do things? And this leads to like important things that we're going to work towards later as well. But at the end of the day, there are these things called 7 segment displays. Now, when we have been, so far when we've been looking at outputs, we've been looking at those like binary patterns at the bottom of our computer, right? Those 0s and 1 signals. Now, the problem with that is, like, look, there's nothing wrong with binary, but, you know, it's harder to, you have to like process, you have to look at the binary pattern and be like, okay, what is that? You have to figure it out. Where if you saw the number like 15, you'd be like, oh, it's 15, right? Okay, that's a bad example. F is pretty easy. But if you saw like 72, 72 is 72. But if you saw a bit pattern for 72, chances are you don't recognize it like that. So, okay, we're making a computer and we want to be able to output values from our computer. A reasonable thing to do. You are all used to doing that. We are looking at the output of a computer as we speak, right? So having a nice, easier to understand output is going to be a good thing. And we're going to use 7-segment displays. So we want to be able to output. There's two problems we want to like solve here, right? One of the problems is the binary. Okay, we want to be able to say, like, look at a decimal, a base 10 number, because it's easier. So that's one of the problems. The other problem is, like, when we're looking at the output of the computer, right now the output is whatever's on the data bus. But that value is always changing. So like if I want to output a value and be like, oh, okay, I'm outputting the value 17. I look at the bit pattern. But then for the next clock pulse, that value changes because it's whatever's on the data bus. That's not very helpful. But this is an easy thing to solve in the same way that we did it with the address register. Remember how the address register, like we needed a way to like isolate a value. We put it into a register. And then we use the value from the register to index RAM. We're going to do the same thing for output. We're going to use a register. So what we're going to want to do is take a value that we want to output, put it into a register, so it's saved there and it's static. It's not transient. It's not, we can change it whenever we want, but it's not going to change with every clock pulse. Its changing is independent from the clock pulses, insofar as like we can control when we want to change it. And then we also want to take the value in that register and output it on the 7-segment display. But we got a big problem with outputting on a 7-segment display. The problem with the 7-segment display is the patterns to output the number like 1 and the binary number 1, let's say we have an 8-bit, 00000001. That's the number 1. We want to output that to a 7-segment display. Okay, hook those signals up to this 7-segment display. It ain't going to work because these 7-segment displays work in a very specific, very simple way. So first and foremost, a 7-segment display is perfectly made up of 8 segments, which makes perfect sense, but it is 7 plus the decimal. Okay? So we have these segments, and they go like this clockwise. A, B, C, D, E, F, G, H. And the signals go A, B, C, D, E, F, G, H. You're never going to have to memorize this. If I ever asked you to do something like this on a test, I would give you like the labeled. You'd need to know that A matches with A, and so on. But basically, you have 8 signals hooked up to this. If E is low, it's off. If it's on, it's on. So now, going back to the example with the binary number 1, it really depends on how we hook up our signals, right? If I have my 8-bit, look, 8 signals, we have 8 bits. Perfect, right? So the number 1, 00000001. The first question we have is, how do I want to hook these signals up, the least significant to the most significant, to those? I probably don't want to go like, okay, A, B, C, D. That's ridiculous, right? We're going to want some nice, more systematic, clean way. So I have a choice. I can either do like, maybe I want to do like A, B, C, D, E, F, G, H. I could do that. Or I could do A, B, C, D, E, F, G, H. I could do it like that. It doesn't really matter. But if this was my strategy, and I wanted to output the number 1, and I gave that bit pattern to the 7-segment display, what would we see? Well, what's an A? All we would see is, if here's our 7-segment display, all we would see is this on. That's it. And is that the number 1? No. Or similarly,
Actually, I think it is in Chinese.
oh, maybe. Oh, problem solved. If we did the other order, what would we see? Well, we would see a dot, which, not great. I mean, if we had the number 3, we would see, for that encoding, and so like obviously this isn't gonna work. We need some translation. We need some way to decode what this pattern is to a pattern for that. There needs to be some form of translation. Do we see the problem at least? Cool. All right. Now, turns out there's a simple solution to this problem, but we're working our way there. I kind of jumped ahead a moment. So 7-segment displays, if I have a total of 7 segments, really 8 segments, but let's say 7 segments, I actually have 2 to the 7, 128 unique patterns that can be represented. 256 if you include the decimal, right? Which makes perfect sense. That corresponds to 2 to the 8, right? So there we go. But a lot of those patterns, at least when thinking base 10 numbers, decimal numbers, a lot of those patterns are pretty useless. When thinking base 10, we have 10 of those 128 or 256 patterns that we care about. The patterns being 0, 1, which I guess we have a couple options, but usually you do it with like these 2. 2 would be like, okay, this one, this one, this one, this one, this, and so on and so on and so on. So although we have a lot of patterns, like the pattern like is not helpful, right? Like this segment and then this segment, right? So we really have a very small set of patterns that we care about. They're called 7-segment. Yeah, usually we have 8. Okay, so this is the idea. Here I'm just kind of like, okay, if I turn them on, we can see how they go. The pattern for 8 is pretty simple. It's just like everything on except the decimal, I guess, but yeah. There's the idea. Any questions about the general idea of the 7-segment display? Now the problem's still clear though. How do we go from the binary pattern meaning a number to the pattern that the 7-segment display actually wants to output? So one could think of these 8 signals as 8 bits, 1 byte, but it's important to remember again that the patterns don't match. So yeah. Here, if we are saying, it looks like I'm going with the pattern for where A is the least significant bit. This is arbitrary, doesn't really matter. There is a design decision why I made A the least significant bit, but you'll see in a moment. So the number 9 is 8 plus 1, 9. That's that binary pattern down there. But if we output that, we would see this, which is, of course, that's not the number 9. So, okay. I mean, if you're psycho, you could learn about, oh, that's clearly a 9 because we know, like, no. But of course, that's not what we're going to do here, because then what's the point of going from binary to something else if we just have some weird, freaky new binary encoding, right? That follows a funny pattern. All right. So in other words, the byte representing 9 as an integer has an entirely different meaning when used to display. Remember, 0001001, it's an encoding of something. How do we decode it? Well, it's a number, and this is a funny one because, like, okay, well, it's an integer. It's the integer 9, yes. But to decode the integer 9, it has different meaning in different, like, we still have different rules on how we decode it based on the context. Okay, so We need some system to convert these binary numbers to their respective 7-segment displays. Their 7-segment display patterns. A single byte can be used for each of the 7-segment display patterns. So, okay, there we go. So here, the display's A input will be the least significant bit, and H will be the most significant. This ordering is a design decision and not a requirement. I already just said this. And below is a table showing what it would be. So if I wanted the number 0, what's the binary pattern for 0? It's that. What's the display pattern? Well, it would be A, B, C, D, E, F need to be on. A, B, C, D, E, F are on. G is not, and H is not. I mean, H could be on, but we're not gonna. So there we go. And what is that in hex? Because it's a little nicer to look at, is 3F. Cool. So 3F, of course, is 0. We all know that. The pattern for 1. Well, 1 is 1, and what do we want? Well, we want B and C on. And that would be 6. And so on, and so on. This is just how do we go from the number we care about to the pattern to represent that number. We're sticking with decimal, though. So 10 is not going to be A. We can make an A with a 7-segment display pretty easily, actually. Right? What would A look like? A. What's actually nice is you could do, all of the hex patterns in a 7-segment display pretty easily. We're not going to, but we could. So there's A. It's a capital A, right? If you don't see it, right? It's an A, yeah.
My motherboard displays hex code.
Well, yeah. So A, B can be like this. C, we have a couple options. We could do something like this or make like a bigger C, whatever. D, and then lastly, E, oh no, not lastly, now lastly, F. We could do that. In fact, if you're like, oh, by the way, if you go into components, we did this yesterday, I/O displays, you could do a hex display, and that actually will take a byte, or sorry, a 4-bit number, and it will do the decoding for us. But we're not doing hex, we're doing decimal, which creates a bit of a problem because if I have the number 10, how do I represent it? I need another 7-segment display. If I have the number 100, which is entirely representable with 8 bits, with our 8-bit system, we can represent up to 255, I need 3 displays. In fact, I also have a peculiarity about like, well, what do I do when I have a negative number? Whew. Right? But we're working towards that. Okay, one may have noticed that 7, oh by the way, this is so nice. This is just a quirk of the universe. The pattern for the number 7 for a 7-segment display is 7, which I think is so nice, right? Isn't that cool? Yeah, 7, 7, 7, it's perfect. There's proof there's a God right there, I think, right? Like, there we go. It's too good. It's a little signature. Anyways. So yeah, 7-segment display pattern for the number 7 is the binary pattern 7. This is by no way meaningful in any way, shape, or form. It's just a nice little quirk. And it really is a consequence of the fact that I picked A to be the least significant bit. I could have done it the other way, then we would have different patterns, of course. But you know, I think that's phenomenal. I love it. It makes me happy. Okay, so back to that problem. Consider how the number 10, which is very easily representable with 8 bits, is representable with 4 bits, right? How can we represent this with a single digit? We can't. If we used hex, we can, but we're showing decimal numbers because the point is to go to a number system that a normal human is happy to look at. You might be happy with hex, but your roommate isn't, right? Like, that's what I mean. So the system being designed can represent 8-bit numbers, a total of 256. So like 0 through 255. Or negative 128 to 127, like we already saw with 2's complement, but more on that later. So a total of 3 digits are going to be required for the system's output. But fortunately, we have a very simple way to deal with this. We'll use 3 displays and 3 bytes for every 8-bit number. What do I mean by this? If I had the number 10, well, let's look at the number 123, for example. This is the binary pattern for 123. So, if I had this binary pattern, remember, if I just had a 3, which is those bits there, I would only care about this bit pattern for the number 3. But I have 123, meaning 123 actually needs to map to 3 8-bit patterns. 3 patterns for 3 different 7-segment displays. Which is, it's a simple solution, but it might feel almost like a little hacky, but no, that's exactly what we need. So, if I have a total of 256 numbers, I need a total of 256 mappings for all 3 bytes, all 3 7-segment displays. One 8-bit number maps to 24 bits, right? 8, 16, 24. But that's just a mapping process. And I saw you were cheesing something yesterday when we needed to map some input pattern to an output pattern. What did you use? A lookup table, exactly, right? Which is exactly what we're going to do, but again, I'm jumping ahead. So since the system works with 2's complement, we need to work with negative numbers. This is achieved with simply a 4th pattern. If I had negative 123, now this actual last pattern here, we really don't need 8 bits for, right? Really what we could do is be like, look, for a negative, if the negative is not on, everything's a 0. If the number is negative, we just need to turn on what? A, B, C, D, E, F, G. We just need to turn on G. That's it. So this last bit, this last 7-segment display, instead of needing 24 bits, we could say, well, let's use 32. For the 4th, no, let's just 25. Okay? 8, 16, 24, 25. That's what we'll do. It almost feels like maybe we could even get away with 22. Does anyone know, like, why am I saying 22 here? Yeah, we don't really need those decimals, but well, that all comes down to how do we want to build this thing. And it's easy to do one or the other, but we'll see. Now, you might remember programmable logic arrays. With a programmable logic arrays, remember that was the series of like AND gates and then OR gates to map any input pattern to any output pattern. Easy to build, simple to build, tedious as hell to build though.
It's like using a bunch of if statements to solve a weak
Yes, that's exactly, it is. It's such like a brute force solution. There's nothing wrong with that. And we're still going to effectively do that, but in a nicer way. So as discussed earlier this semester, programmable logic arrays can be used to really create any logical mapping we want. Any binary function where you want to map some inputs to some outputs, you can make with a programmable logic array. Easy peasy. They're ideal for mapping. They are perfect for this situation. Unfortunately, they scale very poorly with input size. They scale exponentially, which is, ugh. So here is, for example, a programmable logic array mapping 4 bits to only one, or to only the least significant digit 7-segment display pattern. Okay? So this is 4 bits to 1 7-segment display. So this couldn't even, this is what your Minecraft thing could do. I can't even show you the number 8 or 9. But this is a programmable logic array for 4 bits. We have 8. And to get to 8, every time we add 1, we double and double and double and double, right? So this is what it would look like for 4 bits. Oh yeah, and H is whatever, it doesn't matter. Right? H is always off, so I don't care. This is the design. It would be twice as big for 5 bits, 4 times as big for 6, 8 for 7, and 16 times as big for 8 bits. Forget it, right? Not doing it. Now, you may have noticed, by the way, if you've been playing around in digital, and that's how I built this, is digital will actually like generate programmable logic arrays for you. All you have to do is like create the truth table, and then it'll build it for you. But even creating the truth table is a giant pain in the ass. So there's got to be a better way. Okay? Well, it turns out there is, which we already learned about, lookup tables. What we can do is use a lookup table. In fact, one can edit the lookup table easily to enter bit patterns. So what I need here is a lookup table that has 28 bits output, 8-bit input. That means it'll map 8-bit inputs to 25-bit outputs. How many 8-bit inputs are there? Well, however many there would be with 8 bits. 256, 2 to the power of 8, right? This is exactly what we need. Each row, each line in that lookup table corresponds to like the input 8-bit pattern based in order. Starting, the first line will be 0, 0, 0, 0, 0, 0, 0, 0. And then it would have 8 bits, or sorry, 25 bits saying whatever we've got there. The next line would be 0, 0, 0, 0, 0, 0, 0, 1. Whatever 25-bit pattern there is here. Okay? Now, when you open up the lookup table like this in digital, it actually does it as a matrix. So it goes in groups of 8 that way. So really each cell is a row, but it's just kind of like, you know, showing it to you like that. A little easier to kind of wrap your head around, maybe, I don't know. Now here, I'm only manipulating 8-bit patterns here for the output. We need 25-bit patterns, right? So how do I know there's only 8 bits? Well, 2 hex would be 4 plus 4, 8 bits here. But I need 25, so I actually need 25-bit patterns in here. So this is, you know, just for demonstration purposes, not really what we would have. So for each cell in here, I would be like, okay, if the number is 0, 0, okay, what's that 25, what's that 25-bit pattern for that? Okay, well, it's not, it's, okay, 0, 0, 1, 1, 1, and, right, like we would start having to type 25 bits for each cell in here. Now at this stage, you're probably thinking to yourself, is that really better than building the programmable logic array? I have to go to each of these 256 things and type a 25-bit pattern. Really? Yeah, of course not. That's ridiculous. We're not going to do that either. Instead, let's just programmatically make this. We know the system of rules, so let's write a program to generate something. Because these lookup tables, you can load in a hex file, which is just a series of values, hex values. You could actually encode decimal or binary, and it'll read it too. But it's, you know, raw, it's hex, where each line corresponds to each cell, each row in that table accordingly. So if we look up here, 3F, this would be like this would be the hex file for this. I'll show you an example of how one would do this very shortly. Annoyingly, the first line of every hex file needs to be this. I don't know why. I think it has something to do with Intel. Decades ago, Intel said that has to be there, and since then it's always been there. So all of your line numbers are going to be off by 1. Because if you look at like, oh, well, like what line number would this be? That'd be 2. And you're like, well, really it's 1. Well, really it's 0, right? But so everything's already off. You just have to minus 2 to everything because anyways. So we can create a text file where we create the 25-bit patterns in each row here. But of course, we're not going to do that. We're going to write a program to make those hex files. But we'll get there shortly. So yeah, clearly this example is just a little example of like what a hex file would look like, because this is far from mapping each 8-bit number to a 3-digit display or 4-digit display really. That's where we are. Let's do an activity. Give me the following the same, listen up, following the same order where A is the least significant bit, give me the 24-bit pattern for the number 128. I want the bit pattern for the 7-segment display. There should be 24 bits in order where it's 0, 0, 0, 0, 0, 0, 0, 0 is A, B, C, D, E, F, G, H. And if I want the number 128, I want it to be like least significant decimal number, next, next. So the most significant bit would be the most significant bit of the most significant digit. So it should be like the ones, 8 bits, 20, 8 bits, 8s, 8 bits. That's how I want it. Clear? Clear. I'll put this on this just to help a little bit, but of course you can use the website and go to that table. It might be handy. I don't know.